So our next speaker is Orin Lincoln from Georgia Tech, and he will be talking about tools for post-processing analysis of high sample rate radio signals. So with that, I'll hand it over to Orin.
Excellent, thank you. Good morning. Cool. So I'm Orin Lincoln. I'm an undergraduate student at Georgia Institute of Technology. I'm studying computer engineering. And for the talk today, I'll start off talking a little bit about what I'm doing at Georgia Tech, why our research requires high sample rate recording and post-processing tools. So I'll explain the need for that first, and then we'll get into what the tools we're presenting are. But yeah, so I'm on the Intelligent Digital Communications team. We're a vertically integrated project team, which is a collaboration between a member of the research faculty, graduate students, and undergraduate students of a variety of kinds. So it's a very diverse team, and it's great in the sense that they're long-term projects that exist across many semesters and allow us to work on complex problems. And so it's a pretty cool opportunity as an undergraduate student to get to participate in this. My team specifically is using software-defined radio techniques to explore radio frequency spectrum utilization in high user density environments. So for instance, we use the football stadium. The software-defined radio GNU Radio is the software we're using. And so I'll talk more about what that means for us specifically. We've got a football stadium which is very crowded. If any of you have been to a football game and you might have tried to use your mobile device, you might experience limited network connectivity. And so what we're doing is we're actually going into the football stadium, recording how the radio spectrum is used from multiple perspectives of the same environment, and then we're analyzing that data after the fact. So we've got lots of data, and it's important for us to see what is going on actually in the ARC environment, because there's Wi-Fi, Bluetooth, coaxial microphones, lots of things possibly interfering with one another. And we'll do localization on transmitters in that environment. So that's it's critical that we're recording the same data from multiple perspectives so that we can calculate the location of transmitters. And eventually we'll be drawing conclusions about what that means specifically, but we're not there yet. We're still in the data collection process. What we started out with was just sending students individually to different locations of the stadium with a laptop, USRP, and an antenna, and just making recordings themselves. It's funny that maybe have these setups moving around in the stadium, but it's pretty cool. You'll notice also that we recorded metadata about these recordings in the file name of these recordings. So we did 40 plus characters in the file name. You have the center frequency, sampling rate, the time of recording, for instance. So that's what we started with, and it got a little unwieldy. So we had lots of data. During this phase, we actually collected over 2 terabytes of data. And this was last season of the football season. And as an improvement to that, we've designed a network of radio spectrum sensing nodes that are going to be deployed in the football stadium at different locations. So we've scouted locations in terms of what we have accessible for power or network connectivity back to our lab, as well as where we could actually deploy nodes because there's stands, right, there's people. And so these are some of the locations that we've identified. We actually started deploying these nodes to those locations, which we'll get to shortly. But first, what is in a node? This is a picture of the inside of an actual node. It's in a weatherproof case, so that it can be outside, durable from rain and heat, things like that. So inside it's just an Intel NUC, it's our general purpose computer, and an Edis V200 USRP is connected to an antenna on the outside of the box, right? So that's the important part of what we're doing here. These nodes can be deployed outside in the football stadium, and we can talk to them via the network. So and here's actually part of the north stands where it looks like a great place to put an antenna. And so that's what we did. We have an antenna there. It's actually covered up a little bit by a plastic thing. So you maybe people are like, what is that thing looking at us, right? But yeah, so this is the antenna is looking in the north stands. This is the first radio frequency sensor node we deployed, and the actual computing part is mounted on top of a concession stand in the stadium. So given that these things need to be portable, they're subject to swap constraints. That's size, weight, area, and power. So we can't maybe solve all our problems by throwing more hardware such at it. But yeah, so that's the idea. I'll go ahead and preface before I talk any details about our experiences with the data that we collected. Keep in mind that that's the hardware we're using. We've got Intel NUC and a B200 USRP. So the thing to take away from the research problem that our approach to this research problem, we're collecting large amounts of data. So a football game, maybe 3 hours worth of data at a time, for instance. These are large files that we're recording, and we're recording the same environment from multiple perspectives. So we're looking at the same signals from a different location. And using that, we can do time difference of arrival calculations to determine the location of transmitters. So, but to do that, we must maintain precise timing information that corresponds to those data signals throughout the entire time we're processing the data. Okay, so our solution for this, we're introducing GR analysis module, which is a set of tools that leverage metadata headers to simplify the post-processing of large amounts of data. So this is not something we had before. The tools we're looking for didn't quite exist. So that's what we have now. We also are enabling synchronized high-speed, high sample rate recording over extended periods of time. So this is for if we want to record multiple recordings, synchronize multiple recordings of the same environment in a football game. We can do that now. These tools are C code and Python scripts, so they're not any GNU Radio blocks that I'll be introducing to you today. But that's okay. So we'll talk about how these are used in our team and the features that we have now. But at first, you should have some understanding of metadata, why metadata is important. It's just data about data. So the strongest case I can think of, you've got a sequence of digital samples, right? How does that map into a continuous time waveform? Well, you must know the sampling rate, right? It's a pretty straightforward example, but if you've lost knowledge of the sampling rate, you don't remember what sampling rate you recorded the data at, you can cover that later for insert. And other things. So center frequency, where the USRP is tuned, right? Gains, the receive time, especially if you want precise time information. I should have pointed out our nodes include GPS disciplined oscillators, so we get a very precise timing across the nodes as they're deployed in the stadium. In GNU Radio, you heard Tom talk yesterday about the screen tags. Those tags exist when you're actively running slow graph. These tags are passed from the USRP block to, for instance, the tag debug block, right, or the GNU Radio file metasync block, right? It writes these tags. So for persistence, the pieces of metadata are stored as a serialized dictionary of key value pairs on disk. So it's convenient. You can store basically anything in these metadata headers using polymorphic types, which is a convenient feature that GNU Radio offers in the library. And so, for instance, right, we just ask the dictionary, what's the receive rate, and it has a value associated with that. Maybe it's 10 million or something else, whatever the recorded data has. So these headers can be stored on disk either inline or detached. The difference there is that inline headers are interleaved with the data, so there's a header, and then it's immediately followed by data that corresponds with that header. And then there's another header and more data. For these detached headers, it's just another file. So we still have a pure data file, and then another file that contains headers that map directly to the data contained in another file. So that's the difference there. It's pretty straightforward. There's not a difference otherwise. I should point out also these metadata headers contain information about how much data they refer to, right? So that for the inline case, you can differentiate between what's data and what is a serialized dictionary of key value pairs, right? So this the first tool I'll be introducing is a tool for manipulating files called FileMan. There's several uses that we use. The most notable maybe is truncating large data files. So if we just want to look at a little bit of time, then we can take a slice of that file given boundaries in either time or sample number. So then we can extract a smaller amount of data that makes it easier to import into MATLAB, for instance, if we want to do further processing on it. I should also point out that it's often the case when you're describing a slice of data, whether through time boundaries or sample number boundaries. Let's say we want the data between sample 2 million and sample 3 million. It may be the case that there's not a header written at sample 2 million. So it's necessary to interpolate the time step information or the sample number information between headers, so we can trust those numbers and interpolate between there. So that's what this tool does. It's also used on our team for converting between SC16 and SC32. So we might record in SC16, it takes half the space literally, so it's easier to record. But it might be other tools want SC32, so you can easily convert back to that. So that is the file management tool. Again, so if we've got maybe a large recording sitting on a node somewhere, it's connected via the network, we can just pull over a small slice instead of, like, for instance, a 5-minute recording at 25 megaseconds a second. SC32 data is 60 gigabytes, which is huge. You don't want to import that into MATLAB, so we've got to take slices of smaller pieces of it to look at individually. I should point out that the command line term we are introducing is just really just a wrapper for Python functions, so you can use these same functions and scripts that you write. Make header is another tool we're introducing. This is simply to generate headers for data that did not previously have headers. So I mentioned that when we started recording, that was last football season, we had about 2 terabytes of data without metadata headers associated with it. So after the fact, we can create synthesized headers that maybe don't have the same level of precise timing information, but they have some of the information that we used to record in the file link of the data. So now that can be better associated with the data, and it allows us to use tools that leverage metadata headers. So that's useful for us. Again, this script is callable from Python, and you can use the same functions in other Python scripts that you want. But I should also say that just because we're using these command line tools, you can also, once you have data that exists with metadata, and that can go through a GNU Radio flow graph just as easily, right? Using the file data source block, right? So, okay, this other tool, metadata to CSV. This converts metadata that is stored as GNU Radio header format into just a CSV table. That enables the easy import into MATLAB or Octave. So if you are looking at a subset of data, you can easily look at a subset of the metadata along with it. So we've got scripts in MATLAB that do more processing based on the timestamp, like we have it into MATLAB, for instance. There's some standard metadata key value pairs. We have extra ones that we also import into this table from the metadata headers. So I talked more about the post-processing tools that we've developed, but even more interesting maybe is our high sample rate recording tools. So what's the problem we experienced? Well, I highlighted our hardware earlier. In our tests, we noticed that the built-in GNU Radio blocks fail to have the desired performance we wanted. So if we're looking at, for instance, the Wi-Fi channel, 25 megahertz bandwidth, we wanted to record 25 megahertz complex baseband, and we could not do that without experiencing overflow errors, given the hardware that we were using. So we implemented faster tools. So it's not just the file metasync block, but even just the regular file sync without metadata information wasn't able to keep up with the demands we wanted. So our solution to that is a spectrum recording tool, specrec. And this is a command line tool capable of recording both data and metadata at higher sample rates than we were previously able to do. This tool uses producer, consumer model, and we take advantage of concurrency that way. You can see in this diagram, we just have a producer thread that reads the samples from UHD, writes to a circular buffer. The consumer thread then writes those samples continuously in disk. So, and also we have a metadata thread that periodically writes headers as needed if that's an option specified. The important thing, the big win that we have, so we're continuously writing samples to disk. And by that I mean we're forcing the operating system to actually write the samples. So we have page-aligned data, and we're making a Linux-specific call to actually write those pages to the disk. I'll highlight more of that theme shortly, but just as a comparison of capabilities between, this is a script, the UHD RFSN file script either sets up a simple flow graph between a USRP source and a file sync or a file meta sync, depending on the command line options. So you can just record data or record data and metadata. Likewise, our specrec tool is capable of both of those. This is a comparison of sample rates using the hardware I described earlier, and you'll notice that the specrec has significantly extended our capabilities for recording data and metadata. Why is that, right, you might say? So I said our big win earlier is to continuously write data, and that's exactly what it is. So here is an IOStat plot of data that's actually being written to disk, and this is collected for the first 60 seconds of our recording. You'll notice this UHD-RFC file is very bursty. So you have these huge spikes that exceed 500 megabytes per second. You'll notice, and then there's times that drop off completely, right? This is not necessarily the fault of the GNU Radio block. I should point out this is the fault of the operating system. But what we do instead is force the operating system to write continuously, and that results in a much smoother line. It's basically a flat line for spectrum. The takeaway here is that the means of these of this data is approximately equal for the UHD-RFC file and for specrec, but the variance is much larger for the UHD-RFC file, right? So it's very bursty data, and the peaking as high as 500 megabytes per second may not be able to keep up with our solid-state drive writing maximum write speed specification. So I should point out that the storage media specifications indicate the maximum may not be, the device may not be able to keep up with that for an extended period of time. So if we're recording for hours at a time, for instance, the maximum may be only for a short term. Likewise, even if our average rate is below the maximum specified by the storage media, it's very possible that occasionally this bursty spikes that we experience can very easily exceed the maximum specified by the storage media. So by instead continuously writing data, we keep our average rate well below the maximum write speed for our SSD. And that allows us to avoid overflow errors that we were experiencing with the built-in GNU Radio blocks. This tool is not perfect, so it is a command line tool. As I mentioned, it's not a GNU Radio block yet. There's nothing necessarily to prevent this forcing the operating system to write pages of data. There's nothing that prevents that from being implemented in a GNU Radio block. We just have not encountered the need for that yet as a team, but that's definitely future work that can be done. I'll also point out that our metadata writing capability is less rigorous than the GNU Radio file metasync block. So those of you who are familiar with that block, it basically writes the metadata it encounters, also any stream tags that it encounters into headers either inline or detached. We don't have quite the same capabilities yet, but what we have does work for our team. I'll point out specifically, it doesn't respond to any changes in input stream. So because it's not, the spectrum tool is not a block, we're not retuning the USRP while we're recording. Any retuning happens at the start of the next recording, right? So that allows us a simpler, more efficient way to write the metadata, but that wouldn't be a consideration we would have to change for this to be implemented as a block in a flow graph. That being said, we also don't rewrite any existing headers. So if you're familiar with the code or GNU Radio file metasync lock, that code actually, when it starts writing the next header, it rewrites the previous header. Why is that necessary? So if you have inline data and metadata, you need to be able to differentiate between what is data and what is a header. And so once you start running the next header, you can update the reference in the previous header to indicate where the next header is. In contrast, specrec writes headers periodically only, and so we really are trusting that we're going to keep recording right until a certain amount, and there's not necessarily going to be interruptions to the data there. But that being said, we also don't write inline headers. It was a performance risk to pass a file handle between those two threads, and so we're only writing to an extra file for the headers, but we have the information conveniently with our implementation. So that's allowing us to start performing time difference of arrival calculations and determine location of transmitters. There's a lot more types of things that we'll be exploring in the football stadium, but these are some of the tools that we use as a team, and they found them helpful. You might find them helpful if you want them. They are available today. Our GitHub, Paul and Paul's GitHub repository. Here's the link. These slides are posted, will be posted on the website for the conference. So feel free to use them. If you're interested in post-processing analysis tools, we'd love to talk to you and find out about what you're working on. And so come talk to Paul or I about that. Can you work on about that? Yes. And so that is it for the presentation. Probably talked a little too fast, but I'm open for questions.
All right, and we do indeed have time for questions. I asked George to come up and get mic'd here for the next talk as well. Okay, so Sean. Actually, you have 8 people to start, or I need to be more diligent about making people use the mic so we support it.
Yeah, so great talk. I was wondering, maybe you mentioned, and I just missed it, but are you guys using GPS on those PT100s?
Yes. Sorry to clarify, the precise timing information that we're gathering is from GPS system operators.
Okay, so the timestamping comes from the user?
Yes, that's exactly right.
And then the other question I had was your storage. Did you just, basically store it with either the solid state drive? Did you have like an external one, or is it like one of those little one-sided drives? Or?
Right.
Inside the NUC?
Inside the NUC.
It's an unstated drive, but it's just it's got to be large, I guess, the whole 3 hours of data. And then you just upload that later?
There's a terabyte in the NUC, and when we need to take all the data off and the next day, for instance, we open up the server and we can go to.
Okay, so offline you just trickle it out.
Yeah, I think okay. Yes.
All right, thanks.
Okay.
Actually, I had a couple questions too. Well, for the post-processing, I don't know if you guys have, I don't know if Hadoop is something that you guys have considered or thought about using for doing some post-processing. I thought that might be a potential option just because it's exactly what it's for, right? So, I mean, anyways, another thing too is, based when I was doing my PhD in research, one thing that was really interesting to have is usage models like the stochastic models that actually show you, how often people are using. So things like spectrum sharing, right? So if you can track what people are doing and how much the channel is being used, I think this is a really good set of information for doing that because I don't know how often you guys are taking samples, but on previous spectrum sharing measurements like this, they would just take an energy measurement every 1 second and over a long period of time. But you guys are actually looking at a specific event, which I think that's very, very interesting.
Okay, do we have any further questions for Orin? No? All right, a round of applause for our speaker.